Hi, welcome to BC Video 11.1a Part 2, Adding and Subtracting Vectors.
Okay, geometrically you can look at adding two vectors. If you have a vector u, 4, 3 and a vector v, 1, 2, if I added them together, one way to look at it is to put the vector v so that its initial point is moved from 0, 0 to the terminal point of vector u and then drawing it. So basically this vector v is now moved over to this location here as an equivalent vector. Then if you were to take an object, for example, and push it first from 0, 0 to 4, 3, and then you push that object from the point 4, 3 to the point, so that from that point 4, 3 to the point 4, 5, then the equivalent would be to have simply moved it from 0, 0 to the point 5, 5. So it turns out it's the diagonal of this parallelogram that you have created right here. So what happens is if you add the vectors u and v, algebraically it's extremely simple because you had already gone 4 to the right and now you're going to go an extra 1 to the right. So you're going to have 5. You had initially gone up 3 and now you're going to go up an additional 2. So really all you do is add the x components and add the y components. So it's very, very easy to do. The sum of two vectors is not called the sum vector, it's called the resultant vector. So here's an example of vector u and vector v. You don't need to draw them. If you're just asked to add them algebraically, then you'll simply add the x components, comma, add the y components. Now, geometrically, there's two ways to look at it. You can draw, as we saw before, a parallelogram where if it's u plus v, you take vector v and instead of leaving it in standard position, you attach it to the end point or the terminal point of vector u, and then you can draw a parallelogram here, and your resultant vector is the diagonal. So you can either leave it in that position, draw a parallelogram, or if you move it, you get the triangle method, and the resultant vector starts at 0, 0 and points towards the terminal point of the newly moved vector v. Okay, now we're going to look at scalar multiplication, where you are multiplying a vector by a real constant. So, for example, 3 times vector u, let's pretend vector u is the vector 2, negative 1 in component form. Again, very easy to do algebraically. You simply kind of distribute the k, multiply the k by the x1, also multiply the k by the y1. Now, geometrically or visually what this looks like, vector u is here at 2, negative 1. What we did is we made vector u 3 times as long as it used to be and pointing in the same direction because we multiplied it by a positive. So it's now 3 times as long but pointing in the same direction. Vector negative u, the negative of a vector, again you can look at it as multiplying each component by negative 1. What happens now is it has the same magnitude but it's pointing in the opposite direction. So they're like what we used to call opposite rays. They're opposite vectors. The difference between two vectors, algebraically, very easy to do. You'll simply subtract. 2 minus 1 is 1, and 3 minus 5 is negative 2. It's very easy to do algebraically. Geometrically, though, you're going to have to look at it as adding the opposite of the vector. So here's the example. You have your vector u, you want to subtract from it vector v. So the first thing you do is draw the opposite of vector v, which is negative vector v, okay? And then with the green and the yellow, you can do the parallelogram method, for example. So you draw a parallelogram, and then from the origin, the diagonal from the origin pointing to with that opposite vertex is your sum of vector u plus vector negative v. Okay, so putting it all together, this is a subtraction, but we also have two scalar multiplications, so you replace u by in component form negative 1, 3, replace v, distribute the 2. Your choice here, you can distribute the negative 5, but then you need to put a plus. I like to leave the minus and just distribute the 5. and the negative 2 minus 10 is negative 12. 6 minus 25 is negative 19. And of course, it should be obvious to you if you add a vector u with its opposite, you will get the 0 vector.